So we're going to do frozen lake. So frozen lake, you have your favorite frisbee, and you threw it on the lake by accident. It's in the middle of the winter. And because there's an international frisbee shortage, you really have to go on the lake and pick up your frisbee. And the frozen lake is a grid of 4x4 fields. And S would mark, it's like this, 4x4 fields. And S marks your starting point. F is like the frozen surface, which is safe to walk on. And the hole is like you fall through the hole, you fall into the lake. And G is the frisbee, this is your goal, you want to pick it up. And the episode or the game ends, either you reach the goal or you fall into a hole. And you receive a reward of 1 if you reach the goal, and 0 otherwise.
So I need to reach the goal, the frisbee, but I don't have to get back.
You don't have to get back. Okay. So Jim, I'm going to go through the whole code, and then the one that's missing, which fill out, I'll give you some time for that, okay?
Yep.
So NumPy is the mathematical library for Python, random for random number, and Gym is the OpenAI Gym package, where it has all those environments. If you want to load a Gym environment, you say like Gym make, and then you have like some kind of string. The string indicates what kind of environment you want to make. And Frozen Lake is the Frozen Lake environment. And so observation reset, event environment reset, you initialize or reset the environment, and when you do that, it returns you like your state, your current observation. And what you can do for a while is true, so we play just one episode now. I'm going to show you what it looks like. And we're just going to randomly sample the actions, just a random agent, right? And each time it's going to tell us what's the observation, like the next start, the reward, if you're done, and some info variables. And environment render renders the environment. So here the environment is rendered in a string, so it's going to be just some string printouts. And if we're done, we close the environment. We're going to run it, and we're going to see our random agent walking randomly over is in the corner, and then goes down, and then goes right, back. And this is a very long period for a random agent. And then it drops into a hole. So this is again pseudocode for the algorithm. And this is how we do the dynamic programming value iteration. We write a class for the dynamic programming, and it has an init function, and we have like the theta, and we have a discount factor. The theta is the one where you say if it doesn't change enough, you just keep doing the looping s, and if theta is small enough, then you stop. And we say, okay, the f are discount factor, and then self v and self p are the v and the p values. And we say, okay, get greedy policy from v. It's just this part here in the end, when we say, okay, we output the deterministic policy. One step look ahead is just, okay, we input a state, and it returns the expected action value for each action in each input state, in the input state, sorry. And so this just, you have here to say, okay, you have here the update rule for the action value we're going to take out, right? And then in that model, you say myself v is just number of states the environment has. And then while true, you say delta is 0. Then for each state, you just loop forever, like while true. For each state, you loop through all the states. We do a one-step look ahead. We get the best action. We calculate the data across all states seen. And then we use the update function. And then we say, okay, if delta is smaller than the self theta, then we say we break, else we just continue. So you can now code it together, or you can try to code it yourself, whatever your preference is. Who wants to code it themselves now? I say we just code it here. Just a second, I just need to find. Okay, so we do take the best action. We do here the one step look ahead, right? So what was the output? So this gives us the probability in the next state and the reward and whether we're done, right? So it was like the probability of the next state times of the reward plus self discount factor times self dot v from the next state. So this was the update function, right? And I say, okay, well, delta is true. We do a one-step look ahead, and then we select the best action from A. So take argmax from A. So what this does is gives me for each action in the state, right? It gives me like what I expect from the future. This gives me the best action. And then we have to calculate delta.
Can you refer to the formula? Where are we? Yeah.
So this is the formula that is the one-step look ahead.
Mm-hmm.
So this is like the sum. Yeah. So this gives me for each action this kind of score. Mm-hmm. And then the maximum gives me this kind of best action. Maximum of this. And now I need to calculate my delta, which is like the maximum difference between it's the maximum of delta and v minus vs. And when I loop through all the states, I loop through all the states, and I look at my delta for every state. And if it's smaller than theta, I stop. So I need to calculate my max delta, which is the maximum of delta, and NP absolute, best action value. Sorry, this is best action. Oops. Where's the insert? Yeah. So the product max, right? And this best action value minus, I think it's the current value, max self dot v from state s. So s is the state. And then now we have to update it. So we say v like self of dot v of s is best action value. That's it. Let's run this. Can do slippery faults. So slippery just means like if you select a certain action with a certain probability, you select a random action.
Can you say it again? What was the slippery true or false?
The slippery is like you select an action with a certain probability, you do actually a random action.
Okay. You don't end up doing what you said.
Yeah, you don't. It's from the environment, right? So the environment is not deterministic. Isn't this finishing? Something is not right. So it says self vs as action value. So now a slippery is like fault. And this is like where our game world starts. And this is like the policy. It's a deterministic policy. We just take the maximum value function for each state. And you say, okay, if we are here, we either go left or we go right. And then we go, down, or we go right, or we go, if we are here, we go right. And then we go down, down, down all the way, and then we go right to the goal. Like we go like this, and then we go like this. Or we go down here, and then we go here. Say, you go down, down, right, right. And you see here the value function, or those two paths are like equivalent, so they get roughly the same value. Is there any questions for this?
Can you show the code one step look ahead?
Yes. So environment P state A returns you all the next states and the probability of the next state and the reward of the next state. And then it goes through this for each state. So for each action, right? So you kind of calculate this, what is in here, right? You calculate this equation for every A. Mm-hmm. And you return it. You return one of A's. And P is the policy, and V is the value function here. So you go here through for each action, you start at a certain state, right? And then for all the actions in that state, and for all the future states and the probability of the future state and the reward of this future state, you kind of update this probability for each action. Yes?
If there are two possible policies in the real world that makes you end up in the terminal station, I know if there is one optimal policy, it is guaranteed that it converges and you can find it.
Yeah.
But for two, is it guaranteed that you get both right? I mean, because you have value functions and you can traverse it for different policies, right?
So it will find equivalent policies, right? The same value and the same expected return. So then the policies are just equivalent.
So it's guaranteed.
Yeah, it's guaranteed to find the optimal policy. Like in the policy itself, you just do it based on the returns. You go this direction or that direction. This is the trace, right? This is the trace. So you see this? See this? Where it tells you which action to do at every state is the optimal policy. So if you are here, you go here. If you are here, you go here. So this is the policy. Not really, I go this way or go that way. These are not two different policies. So this is a deterministic policy that has one action for every state. And it's optimal. Yes?
There was a question online. Do the properties of the environment are known in advance?
Yes. co-host. It was asked before. I don't know if it got answered.
So essentially, I guess the follow-up question was, are they known or are they discovered, and are there different names for these two if they exist separately?
For the transition probabilities?
That's right.
The transition probabilities for the states are known. They're not discovered. These are part of the environment.
Okay.
So are there any other questions? I think we take a 5-minute break then.
Well, we are out of time.
Huh?
We're out of time.
What do you mean? But we started like 6:30.
How much more do you have left?
Like at least I can do Q learning then.
Like how much time do you need left?
Maybe like half an hour, 45 minutes.
40. Can we go back to the second session?
Sure, we'll just do it at the beginning of the second session.
We can start early next time, man.
When we started it.
We can start early next time, I guess.
I think Steve, you can skip the Monte Carlo and do the Q learning next session before the deep reinforcement learning.
Sure, yeah.
It might work, I guess.
Yeah.
Cool. Thanks everyone.
Sorry, would you post the code in the group, please?
Yeah, post the solution code on the Git. I can post this code for the.
Are we done today?
Still on.
We're taking a nap. I don't want to go home right now.
Is it that bad? Okay. Thanks everyone.